Welcome students to the 6th lecture of the MOOC series on statistical inference. In the last lecture, we were looking at the chi-square distribution, which is obtained as a square of standard normal variate. If there is one such normal, which is x, then we got that x square is distributed as chi-square with 1 degrees of freedom, which is essentially gamma distribution with half and half. We also found that if we look at the sum of square of n independent normal variates, then that will distribute as chi-square with n degrees of freedom, which is gamma with half and n by 2. In this lecture, we will look at some more types of random variables. In particular, the focus of this lecture is on T distribution and F distribution. These are very important for statistical inference with respect to population, and we will see that how they are used in inferencing about population. But before that, in this lecture, I will just derive their PDF. R. A. Fisher has defined T to be a random variable which is the quotient of two independent distribution, where the numerator is a normal 0 1 and the denominator is a function of chi-square. So, let me define it first. Such that x and y are independent. Then a random variable T with n degrees of freedom is defined as x upon root over y by n. X is a normal variable, y is a chi-square variable, therefore, y by n is mean of that chi-square, and root over y by n is equal to square root of that. So, essentially T distribution is the ratio of a standard normal divided by a root mean chi-square distribution. So, what is the PDF of in order to obtain the PDF of T, I will, in order to obtain the distribution of T n, I will appeal to that theorem that we have done in our lecture 5, that if x y is a two-dimensional random variable, then if z is equal to h 1 of x y and w is equal to h 2 of x y, such that the pair of equations z is equal to h 1 x y and w is equal to h 2 x y can be solved uniquely, and the partial derivatives exist and continuous, then the joint PDF k z w of z w is given by f of x y multiplied by the Jacobian, which is the determinant of and this whole thing expressed in terms of z and w, and that is possible because the transformation is 1 to 1. So, given z w, we can uniquely determine the x and y. If we remember this, then we shall use the same theorem for obtaining the PDF of the T distribution with n degrees of freedom. So, let z is equal to x upon root over y by n. Note that this is our variable of interest. In order to use it, we take a dummy variable w is equal to y, okay, because we need to the transformation to a 2D plane, and then as I have shown with respect to the obtaining the chi-square distribution, which is summation of two independent normal variables square. If you remember, we have transformed it to r theta, then we have integrated out theta. So, same thing we are going to do here. Therefore, y is equal to w. Therefore, x is equal to z into root over y by n is equal to z into root over w by n. Therefore, given z w, we can uniquely determine x and y. and vice versa. Therefore, what is going to be the determinant or the Jacobian? This is the determinant of del x, del z, del x, del w, del y, del z and del y, del w. Which is equal to x is z root over w by n. Therefore, del x del z is equal to root over w by n, del x del w is half z by n z by n into half w to the power minus half. And we know that y is equal to w, therefore, del y del z is equal to 0 and del y del w is equal to 1. Therefore, this determinant is coming out to be root over w by n. This is important because this will need in obtaining the PDF of ZW. Therefore, PDF of ZW is f of x y multiplied by the determinant which is w by n expressed in ZW. Now, x and y are independent. Therefore, f of x y is equal to the product of their individual density function, which is 1 over root over 2 pi e to the power minus x square by 2. This comes from x multiplied by y is a chi-square with n degrees of freedom. Therefore, its PDF is lambda power alpha gamma alpha e to the power minus lambda x x to the power. In fact, x becomes y here. So, e to the power minus y by 2 y to the power n by 2 minus 1. It is worth noting that z will go from minus infinity to infinity, because z is a standard normal distribution divided by something which is positive, and w goes from 0 to infinity. Now, this we have to write in terms of z and w, and our transformation was that y is equal to w and x is equal to z root over w by n. So, we are replacing these things here, and this has to be multiplied by the Jacobian root over w by n. So, this whole thing will give me the PDF of z w. Let me write it again. Therefore, k z w is equal to 1 over root over 2 pi e to the power minus x square by 2 into 1 over 2 to the power n by 2 gamma n by 2 e to the power minus y by 2 y to the power n by 2 minus 1 into root over w by n, and we have to replace x with z root over w by n and y with w. Therefore, this becomes 1 over root over 2 pi e to the power minus w by 2 w to the power n by 2 minus 1, and from here we get e to the power minus z square into w by n by 2 into root over w by n. So, this is slightly complicated expression, but this I am doing for you to understand the trick of obtaining the PDF of a function of two random variables. So, let us simplify it to some extent. What we get? 1 upon 2 to the power n by 2 into half. So, 2 to the power n plus 1 by 2 into root over pi into gamma of n by 2 into this root n, let me take out, it is n to the power half. So, we have taken out all the constants. Now, let us look at the variables. So, it is w to the power n by 2 minus 1 plus half. Multiplied by e to the power minus w by 2. From here it is w by 2, from here also it is w by 2, multiplied by e to the power minus w by 2 into, from here I am getting 1, from here I am getting 1, from here I am getting z square by n. So, this is the joint PDF of z and w, which we can write it as 1 over 2 to the power n plus 1 by 2 root over pi gamma n by 2 n to the power half w to the power n plus 1 minus 2 by 2 e to the power minus w by 2 into 1 plus z square by n, where minus infinity less than z less than infinity, and 0 less than w less than infinity. Once we obtain the PDF of z and w, we need to find out the PDF of z from there. How do I get it? By integrating out w, right? If we consider this carefully, we can see that this actually is coming out to be a gamma integral. So, let us forget about the constant first. Let us look at this and let us try to find out what is the integral. I am trying to convert it into the gamma form. We know that it is e to the power minus lambda x, x to the power alpha minus 1. So, I have put it into something minus 1 into e to the power minus half into 1 plus z square by n w dw. And we know that e to the power minus lambda x into x to the power alpha minus 1 dx, that integrates to gamma alpha upon lambda power alpha. So, we are going to use the same thing. Here alpha is equal to n plus 1 by 2, and here lambda is equal to this whole thing. Therefore, this integration is coming out to be gamma n plus 1 by 2 divided by half into 1 plus z square upon n whole to the power n plus 1 by 2. Okay? So, this is the integral of this part. Therefore, PDF of z is, first we have to write the constant, which is 1 upon n to the power half 2 to the power n plus 1 by 2 root over pi gamma n by 2, now multiplied by gamma n plus 1 by 2 upon half into 1 plus z square by n whole to the power n plus 1 by 2. This 2 to the power n by 2 cancels with this 2 to the power n plus 1 by 2. Therefore, what we obtain is n to the power half. Root pi we know is that it is gamma half, gamma n by 2 into 1 plus z square by n whole to the power minus n plus 1 by 2, this divided by gamma n plus 1 by 2. This whole thing is gamma half gamma n by 2 upon gamma n plus 1 by 2 actually follows beta half n by 2, because we know that beta m comma n is equal to gamma m gamma n upon gamma m plus n. Therefore, this can be written as 1 over root over n beta half comma n by 2 multiplied by 1 plus z square by n whole to the power minus n plus 1 by 2. So, this is the PDF of T distribution with n degrees of freedom. Why n degrees? Because in the denominator we had a chi-square distribution which is of n degrees of freedom. Properties T n or T with n degrees of freedom ranges from minus infinity to infinity. T n is symmetric around 0, which is also true for normal, but basically T is more peaked than normal having the same variance. What I mean that the shape of the distribution is symmetric around 0, but if its shape will vary with the degrees of freedom, and therefore, the variance will also keep changing. So, if we take a T distribution with certain variance and consider the corresponding normal distribution with mean 0 and having the same variance, then we will find that T is more peaked than the normal distribution. Another important distribution that I like to cover today is called F distribution. What is an F distribution? Let x1 and x2 be two independent chi-square distribution such that x1 is chi-square with n1 degrees of freedom and x2 is chi-square with n2 degrees of freedom, then x1 upon n1 divided by x2 upon n2 is called F distribution with n1, n2 degrees of freedom. So, basically we are looking at a ratio of two mean chi-square distribution. Before I go for let us compare T n and F. T n is defined as normal 0 1 divided by root over chi-square n by n. Therefore, t square with n degrees of freedom is equal to normal 0 1 square divided by chi-square n by n. We have already seen that normal 0 1 square is basically chi-square with 1 degrees of freedom. Therefore, t square n is equal to chi-square with 1 degrees of freedom divided by chi-square n by n is equal to chi-square 1 by 1 divided by chi-square n by n, and this is precisely f of 1 and n degrees of freedom. Thus, we can see that the square of t distribution also follows a f distribution. So, what is the PDF? As before, we appeal to the previous theorem. x1 and x2 are independent chi-square with n1 and n2 degrees of freedom. Therefore, their joint PDF is the product of their individual PDF, and we can write it as two to the power n1 by 2 gamma n1 by 2 e to the power minus half x1 x1 to the power n1 by 2 minus 1 multiplied by 1 upon 2 to the power n2 by 2. By now, you are familiar with the gamma distribution, and chi-square with n degrees of freedom is equal to gamma with half and n by 2. So, I am simply writing from there, it is gamma n2 by 2 e to the power minus half x2 to the power n2 by 2 minus 1. So, that is the joint PDF of x1 and x2. So, let me write it as 2 to the power n1 plus n2 by 2, gamma n1 by 2, gamma n2 by 2, e to the power minus x1 plus x2 by 2, x1 to the power n1 by 2 minus 1, x2 to the power n2 by 2 minus 1, where 0 less than x1 less than infinity and 0 less than x2 less than infinity. So, this is the joint distribution of x1 and x2. We need to obtain PDF of x1 upon n1 divided by x2 upon n2. So, let us make the transformation. As f is the ratio of 2 chi square, both of them are going from 0 to infinity. Therefore, f is also going from 0 to infinity, and obviously, u is also going from 0 to infinity. Therefore, now we make the inverse transformation. What we get? x2 is equal to u and x1 is equal to f u n1 upon n2. Therefore, let us calculate the Jacobian. Modulus of j is equal to del x1 upon del f, del x1 del u, del x2 del f, del x2 del u is equal to del f u n1 upon n2 del f, del f u n1 upon n2 del u, del u del f, del u del u, this determinant. Now, we can see that this is going to be 0. The Jacobian is u n1 upon n2. Therefore, joint PDF of fu is equal to 1 upon 2 to the power n1 plus n2 by 2 gamma n1 by 2 gamma n2 by 2 into n1 upon n2 f u whole to the power n1 by 2 minus 1, because we are replacing x with n1 upon n2 into fu multiplied by u to the power n2 by 2 minus 1 multiplied by e to the power minus n1 upon n2 fu, because e to the power minus lambda x. So, e to the power minus half x, x is x1 is n1 upon n2 fu into e to the power minus half u. So, this becomes 1 upon 2 to the power n1 plus n2 by 2 gamma n1 by 2 gamma n2 by 2 n1 upon n2 f to the power n1 by 2 minus 1 u to the power n1 plus n2 by 2 minus 2 e to the power minus half u into 1 plus n1 upon n2 f, e to the power minus half 1 plus n1 by n2 f into u. Therefore, this part is independent of u, and if we look at this part, again it comes e to the power minus some positive constant times u into u to the power n1 plus n2 by 2 minus 2, which we can write something minus 1 form. Therefore, this again gives rise to a gamma integral. Therefore, by integrating it, I am not doing the entire integration, I like you to do it. So, the result is going to be n1 upon n2 to the power n1 by 2 upon beta n1 by 2 n2 by 2 f to the power n1 minus 2 by 2 divided by 1 plus n1 by n2 f whole to the power n1 plus L2 by 2. So, this is a fairly complicated expression which gives the PDF of an f variate with parameters n1 and n2. Note that the order of the two constants n1 and n2 is very important. That is, f of mn is not equal to f of n comma m, because f is the ratio of two chi-squared. So, depending upon the chi-square in the numerator and the chi-square in the denominator, the PDF of these will change. Now, you may ask me, why do we need these variates, namely chi-square T and F. Let us first look at chi-square. Sigma xi square gives rise to chi-square. Now, suppose x is with mean 0, then variance of x is actually expected value of x square. So, if I consider a sequence of samples from a normal population with mean 0 and we want to find out the sum of its variance, then we know that the variance of the sum is equal to sum of its variance, because they are independent and therefore, we do not need their covariance, and therefore, we get to know the distribution of that variance, and as you can understand that will give rise to a chi-square distribution. Now, why do we need f? Suppose we want to compare the variances of two different populations. So, chi-square m by m, which is the sum of square divided by the degrees of freedom. So, that gives an idea of the variance of the numerator, or chi-square n by n gives you the idea of the variance of sum of square of normal distribution, or the variance of the population. Similarly, chi-square m by m also give the variance of another population. So, when we want to compare the variances of two populations, we know that variance depends upon the unit. So, as such, the difference between them does not really make sense. The best way to compare them is by taking their ratio and see what is the relationship between these two variances. To compare the variances of two different populations with underlying distribution is normal, we need F distribution. Similarly, we will see later that T can be expressed as a mean upon standard deviation. So, from there we can look at the interesting property of the underlying population when we use T distribution. So, all three of them have come from normal distribution. N actually means the sample size. So, how many samples you are taking from a normal population, and then when we want to compare, when we want to infer about one particular population or want to compare between two populations, we will be using these random variables in an effective way. We shall discuss that in my subsequent lectures. Thank you.